Hello everyone, I'm Ziyuan Zhong. I'm presenting our work on detecting multi-sensor fusion errors in advanced driver assistance systems. This is a joint work with Zhisheng Hu, Shengjian Guo, Xinyang Zhang, Zhenyu Zhong, and Bushaki Rui. Advanced driver assistance systems, also called ADAS, sometimes fail. Recently, it has been reported there are accidents caused by Tesla autopilot, which kill people. So it's really important to test ADAS to improve safety. Now, sometimes the cause of the failure is due to individual sensor failure. And the individual sensor indeed limited under different conditions. For example, camera usually tend to fail to detect the existence of pedestrians at night. LiDAR can be very limited when the rain is heavy. So to address this issue, multi-sensor fusion have been widely used in ADAS to leverage the advantage of different sensors. For example, camera and LiDAR are simultaneously used in the system. The output of the two processed sensors will be output into the sensor fusion module, which then fuse this prediction into a single prediction and output to the downstream modules like dynamic control, and thus provide a more reliable understanding of the surroundings for the ADAS. However, we have found such sensor fusion module can also fail. For example, in this picture, which shows the front camera of a commercial ADAS OpenPilot, it actually fails to detect the existence of a bicycle. However, we indeed found that the radar prediction is correct, actually pretty close to the ground truth, like 3.9 meter versus to 2.9 meter regarding to the longitudinal relative distance with respect to the bicycle. So it can be understood that because the sensor fusion failed to leverage this information provided by radar, and we call such a failure. That is a failure caused by faulty sensor fusion error, and we aim to detect the fusion errors in the current work. Now there are challenges of finding such fusion error. The first one is that collisions caused by these faulty fusion sensors are rare for commercial ADAS. So to find them, we leverage fuzzing with search objectives designed to promote the occurrence of collision and fusion misbehavior. The second challenge is that, fine, right now you have some collisions, but how to conclude the root cause of a collision to be the sensor fusion? So our approach is to leverage simulation and causality analysis to conclude. Overall, we propose a framework called FUSE, Fusion Error Detector, to identify fusion errors. So FUSE consists of three main components. The first component is a fuzzing engine, which essentially is a genetic algorithm. It takes in simulation result at each generation and outputs seed scenario to run for the next generation. It interacts with the second component, a simulation module, which consists of the ADAS as well as a high fidelity simulator. In this case study, we use the OpenPilot, which is a commercial level 2 ADAS, and Carla, which is a widely used high fidelity simulator. The simulation module runs this scenario and output the simulation result to the fuzzing engine. It also outputs the found collisions to a third component, fusion error analyzer, which verify if the found collisions are indeed fusion errors. Now, at the core of fuzzing engine is a fitness function. So we want to find fusion errors, which have two properties, failure inducing and fusion induced, which means a collision needs to happen and the collision needs to be caused by the sensor fusion. So we design a search objective to be a weighted sum of three terms. The first two are for promoting failure inducing. And failure is the Boolean variable representing if the current run leads to a collision. FD represents the smallest distance between the ADAS and a forward leading vehicle subtracted by the ADAS stopping distance. So we want to minimize this distance such that the collision tend to happen. Right? And the third term, which promotes fusion-induced, is the percentage of frames such that two conditions hold at the same time. First is that the output of the fusion module should be far away from the ground truth. That is, the fusion component should be wrong. And second condition is that there exists a best sensor output, which is close to the ground truth, but fail to be leveraged by the fusion component. And then the second part is about the fusion error analyzer, which is used to verify fusion error. So say a collision has been found as shown in this graph, where a collision between the ADAS and the leading vehicle has been found in the current world, that is during the fuzzing. Now, how to verify it? So during the last M-second before accident, a sensor fusion is replaced by a method called bisensor fusion, which essentially output the sensor's output that is close to the ground truth as the output of the fusion module. And if the collision can be avoided in the counterfactual world, then we say, okay, this original collision is caused by the fusion module. Now, how to justify this? We actually build a causal graph. Now, the causal graph is essentially a graphical model that represents the causal relationship between different components. Like say, in this case, we are interested in the collision result. We're also interested in the fusion method used because we're interested in if the method used caused the collision, right? And then the thing come to, okay, what are the other influential factors for the collision? There can be, say, scenario, the simulator configuration, the open pilot configuration. And in practice, we have found that the communication latency also lead to, also influence the collision. And that's a bit problematic because the communication latency is not something controllable. It's caused by the underlying system state, like say the CPU usage, memory usage, etc. But in order to make sure that the open pilot fusion method causes the collision, we have to control all the other influential factors directly influencing the collision. So to mitigate it, we actually intervene by making the simulator communication and the open pilot communication configuration as well as their source code deterministic and synchronous, such that the communication latency won't influence the result of the collision. And during this error analyzer period, we can then replace the fusion method and see if the result flip to determine if the fusion method is the actual cause of the collision. Now, for the experiment, we designed the search space to consist of actors as well as background. All those are searchable. So for background, there are some parameters for weather condition and the lighting condition. For actors, we consider 6 actors surrounding the ADAS. Each actor, we consider them to have different action at different time interval during one simulation. At each time interval, that is each action, the actor can either change line or change speed. Those parameters are all searchable to make the search space relatively large, but at the same time challenging. And for the fusion method we study, we look into the default fusion method, which is a rule-based one using OpenPilot, as well as a common filter-based sensor fusion, which is developed by MathWorks. Now, the next question is, okay, fine, we have found some fusion error, but how to count those fusion errors? There is some might be similar, some might be a bit different, how to count. So here is a fusion error example where there's a collision happening between ADAS and a bicycle ahead. Here's another example. Now, these two look very similar, right? The only difference is that the vehicles on the left line, they are a bit different, but they are not really influencing the behavior of the ADAS, right? Now there's a third one at the bottom where there's a motorcycle way ahead and then there's a collision happen. This one look very different from the first two. So we want to count the first two to be same, but the last one to be different from the first two. How to do this? We actually propose a speed spatial coverage metric, which shows, okay, so what is my speed are different component of the road, and then we can draw this this line, right? And the first two have the same coverage because the ADAS have the same behavior. The third one has very different coverage compared with the first two. So if the coverage is different, then we count them differently. Otherwise, we count them the same. The following are the results. So on the right-hand side, which shows all the found fusion errors, non-fusion errors and non-collision, how they differ in terms of the search objective F fusion. So you can see that there's a huge gap between fusion errors and non-fusion errors. In particular, non-fusion errors tend to have very small F fusion because the majority of the proportion have small F fusion objective value. But the majority of the fusion error scenarios have very large F fusion objective. And this actually explains the left-hand side graph, which shows that our method GA fusion can find more distinct fusion errors than the two baseline method GA and random. So the GA one doesn't have this F fusion objective. The random one is just a random search. The following is a qualitative example. On the left-hand side, a collision happens, and on the right-hand side, during the last 2.5 seconds, the fusion method is replaced by the best sensor fusion, and the collision is avoided. So this one is considered a fusion error. And we also look into the cause of several of these case study. So for this one, we noticed that the Cybertruck on the left line, it is considered the leading vehicle by the camera component. So the camera component underestimates the relative longitudinal speed between the ADAS as well as the leading vehicle. Although the radar one provides the correct output, the ground truth, the fusion output seem to trust the camera. Now, why this is the case, we look into the logic below. So the key step is that the second step where the camera lead has a confidence larger than 50%. So it comes to this step 3, which match the radar output prediction with the camera output prediction. And it's not shown here, but there are actually some other radar cluster prediction which match with the camera. So that one is with the Cybertruck. So that one is actually used as the output of the fusion and resulting in this failure. So in summary, in this work, we define fusion errors and develop a novel gray box fuzzing technique built for efficiently revealing fusion errors in ADAS. We also evaluate the fields in an industry-grade ADAS OpenPilot and show that it can disclose safety issues caused by sensor fusion failure. Thank you.